We will now talk about quotient and how to take derivatives of quotient. We already talked about how to take derivatives of sums, difference, and product. This is the next operation that we yet to discover a rule for. So the quotient rule, as with many things that are quotients, you can actually think of a quotient as a product. So this question is saying, if my function looks like this, f divided by g, and I call this function k, how do I take a derivative of k? Now, in order to not introduce something completely new, what we're going to try to do is actually turn this into a product and apply our already derived product rule, right? So k is just f over g, and I can obviously rewrite this as a product by simply cross multiplying. So I have k times g equals f. And now once that's a product, I can take a derivative of that using the product rule, okay? So a derivative of this, and then the product rule suggests, the product rule will be applied to the left-hand side here. So the product rule suggests that it's the derivative of the first function times the second, plus the first time it's derivative of the second, and the derivative on the right-hand side is just f prime, okay? So this resulted by just applying the product rule. Now the thing that I'm after is k prime. Okay, so I'm actually after this little piece right here. So I'm going to solve this entire equation for k prime. So after a couple of steps that I encourage you to check by yourself, you should get f prime minus k g prime all over g. Okay, so again, this is me isolating for k prime and then dividing through by g. Now, this is what I have so far. My function is in terms of f and g, so I would really like that my right-hand side here only has f, g, and their derivatives. So I have a small problem here that k is still inside there. Now, the good thing about k is that I know that k, well, actually from here is probably better, is just f over g. So I'm going to plug that in for k here. So I have f prime minus k, which is really just f over g times g prime all over g, okay? So notice that this guy here is just k, okay? And now what I'm going to do is do common denominators on the top and combine with the denominators on the bottom in order to not have a double-decker of a fraction here. So I'm going to skip one step in combining all of this together, but please go right ahead and actually work out the algebra. So my quotient rule is going to be just that. If I have a function of the form f over g and I want to take a derivative of it, the derivative is f prime g minus f g prime all over g squared. If you prefer, it might be easier to think of that in terms of top and bottom. So if I take a derivative of the function that is a fraction that is numerator and denominator, top and bottom, then the quotient rule says that it's derivative of the top times the bottom function minus the top times the derivative of the bottom function, all divided by the square of my bottom function. Okay, so this is the quotient rule. Now, let's try this in applications. One of the most astonishing applications of this course is the application of crows and whelks. So crows are, these particular crows are northwestern crows, so the ones that actually live in our region and down in Washington in the United States. And they feed on whelks, which are essentially just these little mollusks. Now, the mollusks are in a shell. That's what protects them from being eaten very easily. So crows, in order to break an actual shell of a whelk, drop it onto the rocky parts of the beach, hoping that it will break. Okay, so what happens if it doesn't? The crow picks it up again, flies up, drops it again. If it doesn't break, it picks it up, it flies up, and drops it again. Biologists have been noticing that crows actually tend to drop whelks from about 5 meters of height consistently. Okay, so crows never fly too low and they never fly way too high. They tend to be around 5 meters of height. And the biologists ask themselves a question: why is that the case? Okay, so in particular, Canadian scientist Rito Zak decided to really investigate this problem. And so he went out onto a rocky beach, grabbed himself a bunch of whelks, and started dropping them from different heights. Okay, so this graph, the data points on this graph are the actual points from one of his experiments. And then he managed to fit a function to this graph, which describes how many drops were required to break the whelk from the given height. Okay, so let's just take a look at this graph for a minute to really understand what it represents. So for example, if I take the height to be, let's say 5 meters, okay, so it's this height here, 5 meters, right here. It says that, so the y coordinate here is, I don't know, approximately 6. So that means that from the height of 5 meters, it will take about 6 drops to break the whelk. Okay, so notice that, of course, the higher you drop the whelk from, the fewer drops are required. So if you drop the whelk from 10 meters, the number of drops that are required is going to be less, like approximately 3. If you drop the whelk from 2 meters, then you require approximately 20 drops, okay? So the height is not very much, but you're gonna have to fly and back and forth quite a bit, okay? So 5 meters seems to be sort of somewhere in between. Now, having collected a lot of data, Rito Zak managed to fit an actual function to it, and this is the formula for that function that describes the number of drops from the height h that are required to break the whelk. Okay, and the question here is to find the derivative of that function, compute it at 4 meters, and interpret that quantity. It is, first of all, a sum of two things. So we can apply the sum rule and take a derivative of each piece separately. Now, the first piece is easy to take a derivative of, but the second piece, of course, is a quotient. So we will have to apply our newly discovered quotient rule. Okay, so first of all, I can say that I'm taking the derivative of 1 plus taking a derivative of 20.4 over h minus 0.84. Okay, and then in the next step, I'm actually going to proceed to take the derivatives. The derivative of 1 is 0 because it's a constant. For the second portion, I'm going to apply the the quotient rule, which of course is given by this formula from the previous slide. Okay, so I'm going to have, so my top is 20.4, my bottom is h minus 0.84. So I'm going to go through the quotient rule carefully. So first it's the derivative of the top, and I'm not going to take derivatives yet. I'm just going to write it out because it's the first time I'm doing the quotient rule. Okay, so the more you practice with it, the more steps you're going to be able to skip. So minus the top times the derivative of the bottom all over the bottom squared. All right, so now that I have it written out, let's take derivatives of the separate components. Okay, so what do we have here? Let's take a look. The derivative of 20.4 is a constant, so the derivative of that is going to be 0. So this guy is actually just going to go away. 0 times anything is just 0. So my first portion of the quotient rule here has actually managed to simplify itself quite a bit, minus, and then I have 20.4 times the derivative of this piece. Now that's two pieces, and our difference rule tells us I can take a derivative of one at a time. So the derivative of h with respect to h, so it's the power rule, the power comes down, so it's 1 times h to the power 0, which is just 1, minus the derivative of 0.84, which is a constant, so the derivative of that is 0, and it's all over h minus 0.84 squared. Okay, so simplifying this just a little bit more, on top I get minus 20.4, and on the bottom I get h minus 0.84 squared. Okay, this is my derivative, so this is my part 1 of the question, and part 2 says find the derivative at 4. So now I just have to plug in 4 into my expression for the derivative. So let me just write this out for completeness here. 4 minus 0.84 squared, which turns out to be approximately minus 2.04. And now what are the units? Okay, if I am to interpret a quantity, I really want to know what the units are. And this is once again where it might be more useful to use the notation, df by dx type notation, right? So as opposed to writing this, I could have written that it's a derivative of my drops function with respect to height. And this tells me that the units on top are drops, the units on the bottom are the units for my height. So this will be drops per meter. Okay? So interpreting this means that at 4 meters, the number of required drops decreases, because this is negative, by approximately 2 drops a meter. And now let's take a look at what that really means on the graph. Well, so if I go from 4 to 5 meters, is that true that the number of required drops decreased by approximately 2? Well, yeah, sure. So this was approximately 7, and now this is approximately 5 on the x-axis, right? Oops. So the rise over run here does look like it's approximately -2. So with every meter that the crow flies higher, the number of drops decreases by about 2 when it's at 4 meters. Notice that, for example, between 8 and 10, the number of required drops doesn't really decrease as much, as opposed to, on the other hand, between 2 and 3, the number of required drops decreases by quite a bit. So this once again highlights the fact that the derivative will really depend on the point you're computing it at. Okay, so this is how one applies the quotient rule when the function is given to you analytically. Let's now take a look at one example where we can apply all types of differentiation rules, but without having a function's formula. So in this case, I have 2 function graphs, a graph for the f function and a graph for the g function, but the derivatives that I am asked to compute do involve a product of these 2 functions, a quotient of these 2 functions, and some kind of a combination of a sum and the product here. Okay? Now, all the same rules apply. It's just I won't be able to compute derivatives analytically here. I will have to get them from the graph. Okay? So the first step here, this is a product. So if I were to compute the derivative of h, I will first of all have to apply the product rule. Okay, so product rule here. Okay, and the product rule says it's the derivative of the first times the second plus the first times the derivative of the second. Now notice that here I'm asked to compute the derivative at a specific point 3. So let me plug that in for x. So it's f prime at 3 times g of 3 plus f of 3 times g prime of 3. And now for the values of those particular pieces, all I have to do is look at the graph and figure out what those values are on the graph, okay? So for example, f prime of 3 here, remember that on the graph, the derivative is the slope of the tangent line at 3. So at 3 here, this is where this point is. What is the slope of the tangent line at 3? Well, I have to sketch myself a little tangent line here, and I notice that the slope here is 0. So this value is 0 times g of 3. Now, it doesn't really actually matter what g of 3 is, because anything times 0 will be 0, but I'm going to write the number in just for completeness. So g of 3 here, if I were to look it up here, this is my 3. G of 3 is actually 2. So this would be times 2 plus f of 3, which from the graph of f, this is just the value of the function at 3, which is 3, times the derivative of g at 3. So once again, the derivative from the graph means the slope of the tangent line at 3. So I'm going to figure out what is the slope of the tangent line at 3. Now, luckily for me, g is just a straight line. So the tangent line to the straight line is itself. So I just have to figure out what is the slope of this line. Well, it's rise over run, and doesn't matter which 2 points you take. The slope of this line will always be a constant, and it's rising 1 and it's running 2. So 1/2. 1/2. So overall, my answer here will be 3/2. Okay, so differentiation rules don't change, but the way that you attain the values for the derivatives and the function values might depend on the representation that you're given of the function, whether it's analytical and you can just plug it in, or it's graphical and you're going to have to read it off the graph. Okay, so for the second part here, of course, I have to do the quotient rule here in order to figure out what this is. Okay, and so I'm going to simply apply the quotient rule first. F prime of x times g of x minus f of x times g prime of x all over g of x squared. Okay, and here I'm asked to compute this at point 2. So I can replace all of my x's with a 2 and figure out what the actual values of those are using the graph, much like in part 1. I'm going to leave this for you to finish off, and I'm just going to talk quickly about the part 3 here. So for the part 3 here, I'm asked to take a derivative of this function, which of course is first of all a product, but then more subtly, a sum, and then more subtly a product, okay? So be very careful about the operations that might not be as obvious as others. So notice that this portion here is actually a product, which means that if you take a derivative of it, you will have to apply a product rule, okay? So let's go through this carefully. So for the derivative here, the sum rule says I can take the derivatives of those two pieces separately. So the derivative of f of x is just f prime of x plus, but now I have to take a derivative of x times g of x. That's a product, so I have to apply a product rule. The product rule says it's the derivative of the first piece, which is just x. So the derivative of x is just 1 times the function g of x plus I leave the first function alone and I take a derivative of the second. Okay, so this is what the product rule on that second portion of the function gave me. Okay, and now once again, I'm asked to compute this at a particular point, 1 in this case. So I'm going to replace my x's here with a 1 and read the values off of the graph that I have to.
One of the applications of the derivatives that we talked about only briefly so far is the relationship between the position, velocity, and acceleration. Here we're going to examine them a little bit closer. So we're going to start with a position function of an object, for example, a runner. That function can be given to us as a function of time. So how far into a particular run is the person at time t? Velocity, by definition, is the rate of change of position. Now, we know that the rate of change means that it's a derivative, and we already have a position function as defined by the previous statement. So velocity is actually simply the derivative of the position function. Acceleration is the rate of change of velocity. Again, we know that the rate of change means a derivative, and we have our velocity function here. So acceleration, usually denoted as a, is the derivative of the velocity that is defined as a function of time. But now let's work our way back here. Velocity itself is a derivative of the position. So I can replace this velocity function by the derivative of f. So what I'm going to end up with is that this is f prime prime of t, right? The first prime coming from the fact that v is f prime, and the second prime coming from the fact that we actually have to take a second derivative to acquire acceleration. So that means that as we're moving from position to velocity to acceleration, all we're doing is taking derivatives of each function to get the next one. So this process is governed by the differentiation here. This also means that if we have a data on distance or velocity or acceleration, we're able to discuss it in terms of derivatives of the previous function. Let's first of all start with units. Distance will be measured in something like meters. Velocity, being the rate of change of distance with respect to time, will be measured in meters per second, right? So we've introduced this per second thing because it's distance per unit of time. Acceleration is going to be the derivative of the velocity, so it will acquire this extra seconds in its denominator. So it will be measured in something like meters per second squared. So now these are the three graphs that describe Usain Bolt's first world record sprint. We're going to start with the distance function because that is the one that we can actually measure the most easily if you have a stopwatch in your hands and you actually witness a runner go. So what we have is time from 0 to 10 and meters from 0 to 100. And what we have are the points, these red points are the actual data points of the fact that at every interval, so here it was actually in 10-meter intervals, where the runner was at every 10-meter interval. Okay, so here we have fit a function to it, and we can look at this graph and answer a number of questions. Like, for example, where was the runner at time 6 seconds? And we can see that he was very close to 60 meters, and so on and so forth. However, what we cannot really tell is where he was accelerating the fastest or the slowest. This looks like almost a line with a constant slope. So we can't easily see whether or not there's a steeper slope on this distance function graph. If we take a look at the velocity graph that you can sketch for this particular data, we notice that there is quite a big difference between when he is speeding or he's running fast and he's running slower. So in fact, we can see that the velocity keeps increasing up until approximately this point right here. So let's actually mark it on the graph right here. And then after that point, the runner seems to actually be dropping his velocity, right? So at this point right here is where the change happens. Up until now, he speeds up, and then after this point here, he starts to slow down. Now, again, what that means is that somewhere at like 7 seconds on the distance graph, if maybe we zoom in, we should be seeing that the slope is steeper before 7 seconds, and then it starts leveling off or getting a little bit more sort of towards plateau. Thinking about what that point corresponds to on the acceleration graph, we can find that it's in fact this point right here. The acceleration was positive up until this point, where the velocity was maximum, and then became negative. So I can actually take the exact same description, of course, because all of my x-axes are in units of time, and I can see that it should correspond to the exact same thing of speeding up until this point and then slowing down afterwards. So what is this point on these two graphs really representing? The acceleration being 0, before it was positive, afterwards it was negative, also corresponds to the exact spot where the velocity was at its maximum. Okay, so let's write that down and then see if we can somehow explain it even further. So acceleration, spelling is hard. Acceleration, there we go. Being 0 is the exact same spot as the velocity being maximum. Okay, so what we need to figure out is how can we think about that in terms of the fact that the derivative of the velocity is actually acceleration. So if I give you just the velocity graph and I ask you something about the acceleration is the derivative of this graph, which means that acceleration is going to be the slope of tangent lines of the velocity graph. So here I can see that the slope of the tangent line is positive and is sort of in the beginning, it's steepest, and then it gets a little less steep, a little less steep, and a little less steep. At maximum velocity is when the tangent line is horizontal. The slope of it is 0. The slope, being the derivative, is acceleration, is exactly what's corresponding to the 0 on the acceleration graph here. Okay, so it's like when you're drawing the acceleration graph, you're really drawing the slopes of all of these tangent lines. They were positive before the maximum velocity point, and then after the velocity starts dropping, so the tangent lines become negative. Negative slope corresponds to the negative values of acceleration over here. Okay, and that is the connection. Now, in general, each one of these graphs will be useful for its own purpose. In this particular example, seeing where the runner is accelerating or slowing down, the distance graph was likely least useful because it was least representative of the situation. And the velocity and acceleration graphs provided much more rich and meaningful information. What happens though if we have a function position given to us analytically, not with a picture, but with a particular function? So we were able to model a process and given an actual expression for the function. So let's see how we can reason about it in a similar way. We're asked to sketch the graph of the position, find the velocity at time t equals 1, find the acceleration at t equals 1. So let's start off by sketching the graph of this function. So this function is t times 5 minus t. This factored out form is good for noting what the roots or zeros are. So what makes it 0 is when t is 0 or this bracket is 0. So this particular function will be 0, and I can sketch that already on the graph. Now, time is likely only positive, so I'm going to focus on the first quadrant here, or the first and fourth quadrant really here in terms of time and the position of the subject. So I know that I have the x-intercepts at 0 and at 5, because once again, this is where this particular function will be equal to 0. But now, what is its actual shape? Its shape is probably easier to see if I actually factor both things out. So I have 5t minus t squared, and I notice that this is a quadratic function, which means it's a parabola. I notice that the coefficient in front of t squared is negative, which means it's a parabola facing down. And I already know the 2 points of intersections that are the x-coordinates. I know that the parabolas are very symmetric, so my graph is going to look something like this. In fact, I can actually quite easily find the top of this parabola because the vertex is going to occur exactly halfway in between the actual x-intercepts at 2.5. I can plug the value 2.5 into my formula here to figure out that the corresponding value for the height is going to be 6.25. Okay, this is all based on my pre-calculus knowledge of what parabolas look like and what their main properties are. Okay, so far, some notes on part 1. We know it's a parabola facing down. It's a parabola function facing down. And if I wanted to write down some arithmetic that I did to find its x-intercept, I know that I have to set y to be 0. So that will mean that I have t times 5 minus t equals 0. And the reason that the factored out form is useful is because that means that in order for the product to be 0, one of the two factors must be 0, which gives me the two roots of t equals 0 and t equals 5. Okay, and I have my entire graph. Okay, let's move on to part 2 of the question. Now we're asked, what is the velocity of the object at time t equals 1? Remember from the previous slide, the velocity is the derivative of a position. So for me to find the velocity at time t equals 1, I need to find the derivative of the position function at t equals time. Now, because this is only the second time I'm seeing this, let me write this down. So the velocity is the derivative of position. So what I need to do first is find the derivative of the actual position function. And I want to make sure that I indicate that this is going to be the velocity function. So I take the derivative of the position. What am I going to get? Now, of course, I can take the derivative in this form, and I will then need to apply the product rule to this. Or I can take the factored out form and take a derivative of this version. Simplifying before you take a derivative is always a good idea. It's easier to simplify than to take derivatives. So I'm going to take the derivative of this version of my function. So here I can see that my derivative will be 5 minus 2t. Now recall that I was asked what is the velocity at time t equals 1, which means that I can plug 1 in for my time right here and figure out this value, and I can see it's going to be equal to 3. I'm actually given no units, which is unfortunate because in all of these problems, usually there are units, but this will be some units of distance divided by some units of time. Okay, so because we have sketched ourselves a graph, it might be helpful to think about what this would represent on the graph. Velocity is the derivative of the position. The graph represents the position function. The derivative is always the slope of the tangent line, which means that this is the slope of tangent line, and not just anywhere, but at t equals 1. So if I draw myself a tangent line at 1, somewhere here, okay, pretty rough sketch. If I draw a tangent line, there we go. The slope, according to my calculations, should be equal to 3. At least it looks reasonable because it's positive. If you ended up with a negative number here, the graphical check will allow you to notice that there's something wrong with your calculations. Finally, what is the acceleration of this object at time t equals 1? So remember that as per the previous discussion, acceleration is derivative of the velocity function, which means that I'm going to take the derivative of the velocity function that I just derived in the second part here. So this is my velocity function. I'm going to take a derivative of that. Okay, so I'm going to write that down. 5 minus 2t prime. And taking a derivative of that, the derivative of 5, let me fix that, it looks like an S. 5 is going to be 0. The derivative of 2t is just negative 2. So overall, I have negative 2 as my answer here. So the interesting thing to notice is that this is now a constant. The acceleration of this object is always constant at negative 2. Okay, the position is changing, the velocity is changing according to their own respectful formulas, but the acceleration remains constant at negative 2. Okay, and that is totally allowed. It can be constant, it can be a function as in of itself that depends on time, but in this case, it's actually constant. Let's take a look at the next application that talks about the Hubble Space Telescope. This is more like a in gratitude to the Hubble Space Telescope because it's currently being overshadowed by the James Webb Telescope that has been recently released into space. The Hubble Space Telescope was launched into the orbit in 1990, and it does remain in operation, although the James Webb Telescope is now taking pictures of much better quality from much further distances. The interesting thing about all of these telescopes is how they actually get launched into space. There's a couple of really interesting points about their launch, and in particular, not only do the scientists have to figure out exactly how fast to launch them into space, they also have to figure out how to fold them very, very efficiently. So one interesting application of origami actually comes in telescope use. These mirrors are not just getting launched into space all fully open. They have to be very efficiently packed so that they can then be unfolded in space when the telescope is launched. The formulas for the actual velocities and the positions of the shuttles and the telescopes are, of course, very carefully calculated and kept. So here we have a model of the velocity of the shuttle during its mission from liftoff at t equals 0 seconds till the solid rocket boosters were jettisoned at t equals 126 seconds. So the shuttle that actually carried the telescope. And this velocity function is given to us by this big formula in feet per second. We're asked to find the initial position of the shuttle and the initial acceleration of the shuttle and the acceleration in 126 seconds when the rocket boosters were jettisoned. So in looking at these functions, it's easy to get intimidated because real-world functions do come with large constants that sometimes muddle the view of the actual function. So the first thing that I recommend doing is searching through the function to find the actual variables. If we do that, we will notice that the variables are present in powers 3, 2, and 1. And everything else in between is actually just a constant. So this is really important to note when you're going to be thinking about the function, and in particular, if we are going to be taking a derivative of it. In fact, here's another rule of thumb in a calculus course. If you don't know what to do, if you're stuck on a question, think, does the derivative make sense in this scenario? Would taking a derivative somehow help? And oftentimes it really does. We're given the velocity, we're asked about an acceleration. Acceleration is the derivative of the velocity, so that's exactly what we're going to do. So first of all, let's find the acceleration function, which is just the derivative of the velocity function. So I need to be taking derivative of this big expression, but luckily this expression is nothing but a cubic polynomial that has been disguised with very ugly looking constants. So in order for me to take a derivative of this, remember that if I have myself a constant, no matter how ugly it is, I simply rewrite it. So I'm going to keep my constant in front here, and then I'm going to take a derivative of the variable term. So t cubed, the derivative is 3t squared. And I'm going to carry on with the same approach. Keep the constant, take the derivative of the variable term. T squared, the derivative is 2t, plus 23.61. The derivative of t is just 1, so I'm not going to bother writing it down. And then finally I have a constant, the derivative of which is 0. This is it. This is my entire acceleration function. Of course, I can multiply through these coefficients in order to simplify this a little bit, but I'm not going to bother because all I'm asked for in this case is find the initial acceleration. I'm also told that initially time was actually counted down from 0, so what I'm interested in is the acceleration at time 0. This I don't even need a calculator for, because when t is 0, this entire term is 0. If t is 0 here, this entire term is 0, so my initial acceleration will be simply given by the constant in this derivative. So 23.61 units. And what are my units? The velocity was given in feet per second. So the acceleration will be in feet per second, which was the velocity per second. Okay? I shouldn't be writing this like this because now it looks like I am going to be canceling out the actual units of time. So let me write it down this way. It was feet per second for the velocity, and then it's per second introduced by taking of the derivative again. So second per second will altogether end up with units being feet per second squared. Now for the second part, I've actually done most of the work. I am asked to find the acceleration in 126 seconds, but I already have my acceleration function. So all I need to do is plug in 126 into this function right here. So the acceleration at 126 seconds is going to be 62.87. And of course, the units are the same, feet per second squared. So what I'm noticing is that in the beginning, the acceleration was 23.61 feet per second squared, and then in 126 seconds, it's 62.87 feet per second squared. So the acceleration has increased, which means that the shuttle is actually accelerating faster going forward. Acceleration is going to be, again, a continuous function because it has to move from one spot to the next. It cannot just jump in velocity or in acceleration and create a hole. It is a continuous value. So I am fairly certain that we can say that on this time period, the shuttle was accelerating faster and faster. Now, this next example is very mathematical in a sense, but it is to highlight how one can approach seemingly easy differentiation, seemingly straightforward, and there's only one right way and one right answer, but in two different approaches. So here we have a function that looks like this, x squared minus 1 divided by x to the fourth. And we're asked to find the derivative in two different ways. The first way is the most visually obvious. There is a division sign here, which sort of suggests that we should be using the quotient rule. So one way, in fact, I'm going to divide my slide into two so that we can compare the two ways really, truly side by side. One way is to simply apply the quotient rule. So I'm going to have to go through the quotient rule formula, the derivative of the top times the bottom, minus top times the derivative of the bottom, divided by the bottom squared. And the second way to do so is to simplify first and then take a derivative. Okay, let's think about how can we simplify this expression. Well, there's only one thing in the denominator, so one way to simplify it would be to undo the common denominator and split this fraction up into two pieces. So what I can do is write down that this is the same as x squared over x to the fourth minus 1 over x to the fourth. And then I can simplify this further by canceling out the terms and writing them down as negative powers if necessary. I'm not going to do this just yet. I'm going to encourage you to pause the video right here and actually do this for yourself. Simplify this function expression and then finish off both sides of my slide here in order to see for yourself how these two different methods will work. Because you are going to have to be the one that gets to pick which method at which point in time you prefer to use. My preferred method might be different than yours, so truly go through to see how the different processes will actually play out. Okay, so let's carry through with the simplification at first. So what I'm going to have is I will cancel x squared and x to the fourth here, and what will end up being is x squared on the bottom and x to the fourth on the bottom here. Now, this I can actually simplify a little bit further still, because I know that the squared on the bottom is actually a negative power. So 1 over x squared is just x to negative 2, and 1 over x to the fourth is actually x to the negative fourth. And now that I've done these simplifications, I can see how easy it's going to be to take the derivative of this function, because I simply need to apply the product rule to each one of these terms. So the derivative now is minus 2x to minus 3. Remember, I have to subtract 1 from the power. So minus 2 minus 1 will give me minus 3. Negative powers become more negative. And then in the second term, I have this negative. I'm going to bring the negative 4 down and subtract 1 from the power. Minus 4 minus 1 will be minus 5. So simplifying this a little bit, minus 2x to the minus 3 plus 4x to the minus 5, and I'm actually done. This is my entire derivative. If you don't like negative powers, you can simplify this to have positive powers by introducing the denominators back, right? So if we really wish to, we can say, okay, well, this is minus 2 over x cubed, and this is 4 over x to the fifth, and I can even do the common denominators and bring these two back together. The common denominator will be x to the fifth, so I know that I have to multiply the first term by x squared. So overall, I'm going to have minus 2x squared plus 4 divided by x to the power 5. Okay, this is now sort of in the exact same form as the original, so this might be good for some specific examples. However, the calculus portion of the problem was done right here. This is where I took the derivative. I've already differentiated everything. After this, we were simply simplifying. What's going to happen with our quotient rule here? Here I'm going to have to take derivatives of all the pieces. So the derivative of the top, one term at a time. The derivative of x squared is 2x. The derivative of minus 1 is 0. I need to multiply now by the bottom, which is just x to the fourth. So I don't really need the bracket here. Minus, I keep the top, so x squared minus 1 times the derivative of the bottom. So the derivative of x to the fourth is 4x cubed. And now I get to divide all of this by the bottom squared, x to the 4th all squared. Now my calculus portion of this question is also done right here because I have taken all of the derivatives that I need to, and I'm sort of in the exact same spot as here. If I'd like to simplify, I have to simplify this expression as opposed to this expression. And I can do so just to at least see if my answers match up. So what I'm going to do is multiply everything all the way through. So 2x to the 5th, combining the powers here, opening up the brackets here. What am I going to get? Minus 4x to the 5th plus 4x cubed. Okay, being careful about the negatives. Divide it all by x to the 8th. Remember that raising a power to a power is multiplying the powers. Now I note that I have two similar terms here, so I can bring the two of them together. Minus 2x to the 5th plus 4x cubed all over x to the 8th. I notice that I can factor out some x's from the top. Don't go ahead and start canceling pieces at a time. You can only cancel things if they're factors of top and bottom. So the largest factor I can take out from the top here is x cubed. If I take out x cubed, I'm left with 2x squared plus 4 divided by x to the 8th. And now I can cancel out some of the powers, which will finally bring me to minus 2x squared plus 4 divided by x to the 5th. And this is excellent news because this is exactly the expression I had before in the other way. The actual approaches might be different, but of course the answer better be the same if simplified far enough. This is why I was saying that it's important that you go through both of the methods to figure out which one you prefer. In different questions, different methods would be preferable. If all you're doing is finding a derivative, this is certainly the fastest way to go because you would have stopped right here and you have only two terms to deal with as opposed to the entire big fraction that the quotient rule will inevitably actually birth. However, if what you need is to keep the fraction together, like we will see in lots of graphing examples later on in the course, it might be worth it, instead of getting rid of the fractions and then reintroducing them again, to keep the fraction and deal with the fact that you're going to be working with higher powers of x all throughout. Okay, it's completely up to you. We're going to take a look at two more applications here. This one is straight from one of the midterm tests from the old course offerings. So I encourage you to pause it and go through this by yourself. There's really nothing surprising here. You have a function that is a fraction. And in fact, if you look at it, you will recognize it as a linear Hill function. You are given the description of it in terms of context. You're asked to compute two values and interpret them. So what is it that they represent? Come up with units and try to think of the differences in numbers and what they mean in the particular context. I'm not going to go through the actual solution here. This is pretty straightforward. I encourage you to go through this yourself. I'm going to go through a bit more of an analytical example that contains constants and not actual numbers for constants, because this is something that sometimes confuses people when they have to deal with letters. So here we have bee foraging for nectar in a patch of flowers. This is a problem that we're going to see later on in the course in an optimization scenario as well. It's very clear that as it forages, it gains energy. We've seen this already in our example of hummingbirds as well. And we're going to assume that the amount of energy gained during foraging is described by this function. The time spent on the flower is given by t. E and k are positive constants. Even before we get to any of the questions, we once again recognize this function as a linear Hill function, and we can already see what it looks like in terms of the graph, right? So we know that the graph of it will look something like this. It will exhibit a linear behavior near the origin, and it will plateau towards a horizontal asymptote at the end. This makes sense because if the bee stays on the flower for a very, very long time, it essentially eats all of the nectar and no longer gains a lot of energy from it. Let's take a look at what the question is asking. The first part asks specifically that if the bee stays on the patch for a very long time, how much energy can it gain? But this is a little more quantitative. Exactly how much? So for a very long time, in mathematical terms, will represent the fact that we're interested in the time going toward infinity. Again, not really truly realistic, but the functional behavior is going to be described at the end with time going towards infinity. And so what I'm interested in here is how much energy, or the actual limit of this function at t going to infinity. So limit as t goes to infinity, et divided by k plus t. Remember that limits at infinity is where we can utilize our power domination or power analysis. So this is, again, bringing back a very useful tool when it comes to computing limits. So what we have here is towards infinity, we're going to analyze the top and the bottom separately. Towards infinity, that's for large values of t, which is where larger powers dominate. On the top, I don't have a choice. I have to keep the only term that exists there. But on the bottom, I have two different terms, a constant k and the variable t. It's extremely important here to remember that t is my variable and everything else is a constant. Okay, so I only care about the powers of t that are present here. The higher power of t is the one I get to keep. So I'm going to keep the t because the constant has the power of t equals 0. Now I note that both t's will cancel and I end up with limit as t goes towards infinity of my constant e. Limit of a constant is always the constant itself, which is e. So this will represent the maximum amount of energy that it can gain. Okay, maximum amount of energy, which is some constant that will likely depend on the type of flower on that particular patch. Next up, calculate the rate of energy gain while foraging on the flower patch. The rate of gain means we are after the derivative. The moment you see the rate of anything, you know you're interested in the derivative of the given function. So I need to take a derivative of my function f here, which is given to me by this formula. Remember, once again, that e and k are constants and t is my only variable. This is a quotient, so I am going to apply a quotient rule. So I need to go the derivative of the top. I'm going to write it out in steps first and not take it. So the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. So k plus t all squared. And again, remember, t is the only variable. Everything else is a constant. If it makes it better, highlight t in some different color, just to remember that this is your only variable throughout. And just because everything else is a letter doesn't mean that it's not a number. Okay, we're going to treat e and k as numbers. So the derivative of e times t. E is a constant, so I'm going to rewrite it and then take a derivative of t. The derivative of t is just 1, so this first term produces just e. And then I have to keep the k plus t here as the factor. And then I have minus et times the derivative of k plus t. K is a constant, the derivative of that is 0. The derivative of t is 1, so I simply have times 1, which I don't need to write down, so I can keep it as is. Divided by, and on the bottom, I don't need to take any derivatives. I can simply keep my k plus t squared. Okay, if I open up the brackets here, open up the first brackets and then maybe do the similar terms with the second term, what am I going to get? I'm going to get ek plus et minus et divided by k plus t squared. And I can see that on top, of course, the two terms containing et will cancel each other out. So overall, on top, I'm going to have e times k divided by k plus t all squared. Okay? That is my derivative. Since we're having a context here that we can put the derivative into, let's think about units. So my derivative is always rise over run. Or you can think of that again as df by dt. So the units of f divided by the units of t. The units of F are some kind of energy units, so amount of energy. And on the bottom, we're going to have per unit time. So per time unit. Okay, and that is our derivative. We notice here actually that we started off with a function that was linear Hill function that had my variable on top and bottom. We ended up with the derivative that only has the variable on the bottom. Another interesting observation here is that E and K are both positive. So this term on top is always positive and the bottom is always squared, which means it's also always positive. So that indicates that this derivative will always be positive. Remember that positive derivative means positive slope of a tangent line drawn at any point in my graph. That means that my graph is always increasing. It might be increasing slower and slower as time goes on, sort of diminishing returns kind of scenario, but it is constantly increasing. And that is something that even without the particular values for E and K, I am able to see immediately from my calculations of the derivative.